Okay, good morning. Thank you, José Luis, for the presentation. It's a pleasure for me to begin with this workshop today. Welcome to Seville again, and I hope you have a spare time to enjoy the city, which is for those who has not been here before. I hope you will find it very interesting. Some very nice corners, Santa Cruz district, and the downtown area, which is very nice. So I will try to present a brief overview of the main challenges we are facing with the hopefully massive introduction of renewables in the remaining part of this century. So I will devote some minutes to introduce the current status and future prospects of renewable integration in the three levels: generation, transmission, distribution, and the technical barriers to be overcome, the hurdles, the challenges. And then the second part of my presentation will be devoted to also presenting in a very brief way the major technologies that, according to our experience, will be fundamental to overcome those barriers. So there will be basically two parts or three parts. I was expecting, by the way, a bigger screen. So we are usually lecturing in other room with bigger screens. So I regret if you from the back from the rear of the room, maybe you will not be able to read some of the fonts, because I was trying to use large fonts, but okay. Let's see. So this is the situation that we have been enjoying so far, which is basically almost 80% of thermal generation so far. This is 2013, so very recent, and the situation now is very similar, a little bit better. And from the 21% renewable, a majority comes from hydro. Hydro is majority, and then only around 4.5% from solar, wind, and biomass. Okay, so this is basically the situation in 2013. Now it's a little bit better, but not so much. What happened with this 78 or 80% thermal? The efficiency is very low. So we have been relying on centralized generation with efficiencies which are on average lower than 55%. So the best thing we can do is combine cycles, and then on average is 31% the efficiency, which is horrible. Which this means that we have been wasting to the atmosphere, to the environment, 2/3 of the primary energy. We have, for instance, taken advantage with distributed generation, for instance, like in Denmark. For instance, in Denmark they have almost 50% of cogeneration and trigeneration, with the efficiency is much better. But this distributed way of the generation has not been very popular over the last century. So this is a big problem. So for over 100 years we have been wasting a lot of primary energy, fossil energy basically, and nuclear. Okay, so this is the origin of the problems we are now facing. Basically, this is the main origin of the problem we are facing now. One of the problems is the exponential increase of CO2 concentration in the atmosphere. In 2013, we exceeded 400 parts per million of CO2 concentration in the atmosphere. And now, 2 weeks ago, I read in the journals and the magazine that we have over 413. So it's increasing, continues to be increasing in spite of the effort to reduce the emissions. So this is a big problem. Over the last 100 years, this has been multiplied tenfold by 10. So this is a huge problem. This is what the scenarios, the IPCC, the scenarios they are considering in the future, from the most pessimistic one, which is if we didn't do anything, if we continue, without doing anything, with current policies, with the agreement in Paris, COP21, and what we should ideally do. The green one is the scenario, the ideal scenario that, according to what we should do to try to prevent from 2 degrees increase in temperature. This is a final concentration of CO2 at the end of the century. These are expected on average temperature increase from the beginning of the industrial era. So this is very unlikely that we are the red one is the Paris Agreement, and it's very unlikely that we will succeed in spite of the efforts in achieving the controlling the temperature increase. So we should prepare for the worst. I mean, for over 2 or 3 degrees increase by the end of the century. So this is a problem. This justify why we are putting so much emphasis in renewables and in this project, by the way. So as a way of integrating renewables in a distributed manner. Okay, so it's clear, therefore, that we need an urgent CO2 abatement or reduction of concentration of emission and then concentration in the atmosphere. And there are basically, I have gathered here basically 6 ways, of which I believe that only the first 3 are really have really a chance to be totally useful. The last 3 probably is doubtful, at least doubtful. So massive renewable penetration, which is clearly what we are trying to achieve. Also electrification of other energy uses like transportation, cooling, some industrial uses that are using gas, natural gas or fossil fuels, and energy efficiency. All these 3 items are being dealt by the European Union in a very seriously with the wind energy package, the winter package. So this other options are not so clear. That's why I have been using big question mark, because it's not clear whether carbon capture, for instance, will be very, unfortunately, it's still undeveloped, and new biofuel also suffer a lot of criticism about biofuel. So not to mention nuclear power. So these 3 options should also be part of the solution, but I'm not sure if they will be in the end. So we should focus on this, and the first 3. Okay, so in this movement, in this shift from fossil fuel to renewables, the wind energy were the pioneers. You may remember that 500 years ago in the Quixote, in the Cervantes novel, they were mentioned also the windmill, the windmills, that also in Holland, for instance, very popular windmills. So it's very, very old technology used for other purposes, but can now be used for electricity generation. Here, near here in Gibraltar Strait, 30, 40 years ago, they erected few kilowatts small machines, like these prototypes of this. But now in the same area, basically in the same area, we can see these huge machines of 1 megawatt or even larger, hundreds of them, many megawatts. So currently there are about 300,000 turbines in the world, of which, for instance, 110% are located in Germany, about 27,000 turbines increasingly in Germany, or with an average power of 1.7 megawatt on the size capacity. So this is the pioneers in renewable generation. And in the last 10 years, the global capacity, cumulative capacity installed has been growing significantly and has been multiplied by 5.7 in 10 years. Now we have over 400 gigawatts of wind energy worldwide installed, cumulated. So also it's interesting to mention that wind energy, the energy per surface is rather small onshore, which is around 2 watts per square meter at an average speed of 6 meters per second. It's not very high density, but it's enough because you can use the land for other purposes. In offshore it could raise to 5 or even larger. But in the opinion of most experts, photovoltaics will be winning the race for renewable sharing of energy mix. Because it has the significant advantage in terms of modularity. So the funny thing is that with a very small cell like this, you can build a module, 400 watts module, and then by putting together many modules, you can have an array of even 100 square meters, the largest one. So modularly, you can scale the system and achieve from the roof of your house to your, several hundred megawatts, as we will see in the next slide. So this is the main advantage of photovoltaics, which can be fully distributed and fully centralized, both. So, and the density is higher depending on the place, of course. It is not the same Germany that the Mojave Desert in California, so it's different, no? But you can achieve very high densities, of 25 watts per square meter. In fact, there has been a boom of PV energy capacity. In the last 10 years, PV started about 10 years later than wind energy. But in the last 10 years, the PV capacity has been increased up to over 200 gigawatts, which means multiplied by 34 compared to 10 years ago. For comparison, the number of smartphones has been increased by 1/2, 17 times. I want to show you here the record, what is currently the record in terms of size, to show you that PV can be as big as a nuclear reactor. In this case, it's in China, in this, I don't know how to pronounce, Longjiangxia Dam solar park, which is here in close-up. And if you can see it compared with the dam, this is the station, 27 square kilometers, 850 megawatts, and this is, they are working together. This is a hybrid plant in which they coordinate the hydro with the PV, which is a very nice arrangement. Combining hydro, which is a way to, you don't need the storage, you have the hydro, okay? So this is a very good solution. And you can see also that the plant, this hydro occupies nearly 400 square kilometers. So it's not so bad. It's not so bad having this power with 27 kilometers and this capacity to 1,200 megawatts for 380 kilometers. Well, this was the record until a couple of months ago. Now there is in India there is a larger plant with 900 megawatts, which is the typical size of a nuclear reactor. So we are now approaching with renewable the same in a single installation facility, the same size as a nuclear reactor. Of course, the energy production is not the same because the capacity factor, for instance, in this case, is not very good. It's only 11%, slightly higher than in Germany, for instance, but much worse than in Spain. In Spain, we have about, on average, 20% capacity factor, and in this region, in Andalusia, in the south, we have a 22, 23%. So this is not a region with probably so much insolation. And this is the other side of the other advantage of PV. This PV can be fully distributed at the same time. So this is totally related with the scope of this project, and then you will talk probably much later about this. So this is distributed generation, for which PV is the best suited technology. Of course, the amount of distributed versus centralized is a big unknown. Nobody knows in the future which proportion, which share will be centralized and which share will be distributed. In our opinion, both will have to coexist, but it will depend on the regulation. For instance, in Germany, because of the regulation, around 80% is distributed and 20% centralized, which is the opposite in Spain, because of the regulation again. In Spain, the regulation promoted big facilities rather than rooftop installation. So in Spain, it's just the opposite. 80% is centralized, roughly speaking. So this is a big unknown, and this is important. This is important in terms of the need to develop transmission infrastructures and many other things. So the amount of distributed and centralized will be important. In the past, most generation was centralized. And so the current system, transmission distribution system, always this history, the centralized history. But in the future will be very different. And this context, microgrid will play a very big role in the future. So this is an example of success, just to give you an idea, in order of decreasing time period from annual, monthly, daily, hourly, and instantaneous. For instance, in Denmark, the record was 2015, 42% of demand was from wind. Well, in 2016, there was a decrease after 7 years of increasing. because there was, in 2016 was a year with not so much wind. So there was from 42, in Denmark they passed to 37. In Germany, for instance, this is October, very recent. I modified my slide yesterday to add this data. Because October has been a very special month in Central Europe because of two big storms hitting the continent. So in Germany, it was very good for them, apart from the problem with the population and but it was good in terms of renewable production. In that month, 44% of demand was covered with wind energy. Okay. In Portugal, for instance, last year in May, for 4 consecutive days, 100% renewable, of course, including hydro. Germany, again, hourly renewable record was 78% of demand in July of 2015. And in Spain, this is still a record. I checked yesterday with Red Eléctrica, this is still the record. In 2015, that was a very good year for wind energy. Over 70% of demand in Spain early in the morning, was covered by wind energy. This leads to very complex situation for the system operator, transmission system operator, but they have been able to manage this high amount of penetration of wind energy, considering that Spain is a not very well interconnected country with the rest of Europe, because the capacity of interconnection is now around 5-6%, which is not so good. It's lower than what European Union is promoting. Well, this boom of PV installation and wind energy installation is leading to a maturity and cost reduction. And you can see here some examples of auctions. The world is moving from feed-in tariffs to capacity auctions. So this is an example of prices achieved in auction that took place in 2016. For instance, in Morocco, the wind energy was assigned at $30 per megawatt hour, which is even much better than coal station probably. Where in Denmark, offshore wind was $54 per megawatt hour. Solar in Chile, for instance. Well, I had Chile, but I had to remove some data. But for instance, Mexico, or here in Mexico, $32 for solar and $36 for wind. So, these are very impressive figures. We were thinking 5 years ago it was impossible for us to believe that we were going to reduce the prices so much. Well, but be cautious. Auctions assignment is not the same as actual leverage cost of electricity. The cost of electricity, according to IRENA, the renewable agency of the International Energy Agency, is bigger, but still, on average, in 2016 again, on average, the LCOEs, the leverage cost of electricity, are very, very attractive also. For instance, onshore wind is $50 per megawatt. It's very good. It's competitive probably with combined cycle. So the prices have been reduced significantly, and this making this attractive and competitive. And in many countries, we are reaching the grid parity. Of course, the disadvantage is that we need storage. This is something we talk about later, because if this trend continues, at some moment we will need to resort to big amounts of storage. Okay. Well, there are many challenges, and I will talk later that the next presentation will be about the technical challenges. But before entering the technical challenges, let me just give you a brief idea of the main challenge, in my opinion, which is not technical, but probably financial or economic, which is the huge investment that we have to face in the next 50 or the next 70 years, if we want to move from a fossil-based system to a renewable-based system. I'm taking as a reference 2015. Okay, this is the data I have. And then this is forecasting for 2015 according to DNV GL Energy Transition Outlook. I can stay 20 minutes about this slide, but I just summarize. The first thing is the electricity demand will be multiplied according to the forecasting, to this outlook, over 2.4, which is strange because we are talking about energy efficiency. So if there is energy efficiency, okay, Energy efficiency means that we must electrify the consumption. So many transportation and industrial processes will have to electrify. So overall, the primary energy may get reduced, but the electricity will increase accordingly. Overall, the primary energy will be more efficient because we are moving to electricity electrical world, electricity consumption. So, okay, so this small, about 4% of energy per petawatt hour per year. This green small is around 4 or 5% of energy coming from wind and solar. Remember that in this year we had 670 gigawatts of wind and solar. And the rest was by fossil, nuclear, and hydro. I'm including hydro here because hydro will remain essentially constant. Okay, hydro will be this one. It will not increase so much. So hydro is included here. Big hydro. So we have to reduce, according to the Paris Agreement and the like, we will have to reduce the amount of fossil, nuclear, and hydro will remain constant, basically. So we have to increase significantly the share of renewable from this small green line to this huge green line. This means that we will reduce by 2/3 the fossil fuel capacity from over 500 gigawatts to 3,500. Accordingly, we will have, and this is the impressive figure. This is the impressive figure, in my opinion. We will have to increase the current installed capacity times 40 to nearly 27,000 gigawatts of wind and solar in order to produce this energy with the current capacity factors, which is about 30% for wind and on the average 11% for PV. So this is multiplied by 40. What does it mean? This means that we should build around 750 gigawatts per year of wind and energy with a cost of 1,000 billion per year, billion American billion, or 1 European billion. So 1,000 American billion is 1 European billion per year. Just to put it in perspective, the last year we added only 132 gigawatts on wind and solar. So we have to multiply by 6 the current rate of increase of global capacity every year on average to achieve this. So this is a huge investment challenge. 1,000 billion per year for the next 35 years. And this will not be 100% renewable. We still will have a significant share of fossil and nuclear. Anyway, this is a terrifying, somewhat terrifying figures. Well, in spite of that, there are some optimistic people, like this guy Jacobson Group from Stanford University. You may have heard in the news, when you are having coffee in the morning, you may read the journals and the newspaper, and you may read that Jacobson Group, for instance. I read yesterday, for instance, that Jacobson had sued, has a legally sued the opponent, the scientific opponent, which is something strange because scientific disputes should be solved in the journal, not in the trials, in the juries. No? So anyway, so these are the one very popular image created by this group. This is they call the Solution Project, which is backed up by very big companies like Tesla, for instance, and they believe that we can create a 100% world in 2050, which is probably very questionable. I don't believe this can be done as they say here, because, for instance, they assume that hydroelectric can significantly increase, which is not the case in most countries. Hydroelectric is probably fully developed in most countries, so I don't think hydroelectric is going to increase and can be used the way they assume that can be used for storage, because hydro is used for many other purposes, irrigation, population, drinking, and the like. So they make some assumptions which are very questionable. So I don't think. And on the other hand, they think that the total demand will decrease by 40% because of the electrification. Okay, so the electricity demand will increase, but the overall demand will decrease by 40%, 42%. Okay, this is a current status and prospect and some opinions. And now let's move to the technical barriers at the second part of the presentation. Well, I have divided the technical barriers by the three major levels: generation, transmission, distribution. Although they are coupled, for instance, generation and transmission, it is doubtful whether it is affecting generation. It is affecting both generation and transmission because they are tightly coupled. So on the generation side, there are short-time, real-time problems regarding frequency regulation. Because the renewables have very low or even null inertia, they cannot contribute to synchronizing power, unless they have a storage, and they have relatively limited capability to regulate active power unless they have storage, of course. In the daily energy balance, I will show you some examples of these problems later. There is no correlation between the renewable production with the demand, and also very important. There will be more volatility. There will be sudden changes of wind energy, sudden changes of solar energy. For instance, when there is an eclipse or something like this, so there will be many more and deeper gradients of net load. Net load is the difference between the gross load and the renewable. Okay. And most important, I think this is most important, we have not been paid, in my opinion, proper attention by this Jacobson proposal or Jacobson reports, which is the need for seasonal storage. I mean, there is an excess of solar in summer in the northern hemisphere, and there is a deficit of solar in the winter. So somehow we should store excess energy and then use it in winter. No, this is a very exigent. For instance, in Spain, according to some very simple analysis, Spain is consuming every year around 240 terawatts hour, and about 10% should be stored in summer if we had a system exclusively based on solar, for instance. So this is difficult to achieve, which is a lot of energy. So another problem affecting generation is that the wholesale markets that were introduced late in the 20th century, in Spain, wholesale markets started in 1998. So those markets were designed when we didn't have renewables. So they are not prepared, they are not well designed, and they are suffering from the high penetration of renewable. So in Germany, for instance, there have been many times where the prices have been negative. And in Spain, many times the prices have been, not so frequently, but sometimes the prices have been zero because it's not allowed to get negative. So generators should pay for producing instead of being paid with negative prices. So the markets are ill-designed for renewables, so they should be designed. And the European Union is now working also on this problem, designing future energy market, wholesale market. So this is some example of what I will illustrate what I've been saying. This is in Australia, for instance. In addition to the normal low gradient early in the morning, we will have now a big gradient when the sun sets. So there will be very huge gradient. And no matter how much PV you introduce, you will probably continue having the same peak loading in the evening. So, and this happens in many countries. In Spain, also the same. In Spain, we have in winter the night peak, and this peak cannot be solved with the PV, with solar. Another example of the effects of wind energy in this case. This is this very popular low duration curve. This is the low duration curve for a country which a maximum power is 20 gigawatts and a minimum power of 9 gigawatts. This corresponds, for instance, to Sweden, the country which is smaller than Spain, Sweden, or even Poland. This is typical, 20 gigawatts, medium-sized countries. So this is an analysis of what happens if we add 2, 4, 6, 8, 10, and 12 gigawatt of wind energy. What happens is that the peak power basically remains unaltered. We only reduce the average load for the minimum, of course. And we may even be negative. Our negative load, the average will reduce, but the peak will remain basically unaltered. So this is a big problem because no matter how much wind you introduce, the peak power remains basically the same. And we saw the same with PV. So this is a huge problem for generation system. It's an example of Germany in January. In January this year, for a week, and you may see here that you may have moments with lot of wind, lot of sun, lot of wind, no sun, lot of sun, almost no wind, and no wind, no sun. So you may have everything in a week. You may have everything, even in a day. In a day you may have everything. This moment, for instance, even if they have 80 gigawatts of renewable, 86 gigawatts of renewable, they have at the end of 2016, they have 86 gigawatts of renewable, with 21% of energy share in 2016. This week, right at this moment, basically renewables was almost null, almost zero, so no renewable here. This is a very clear way of showing the imbalance. This is the theoretical PV production in Germany in July, and this is in January, and this was the actual production in a cloudy day. A cloudy day was 10th of January here, and 10th of July here. Both of them were cloudy days. So this is theoretical, and this is the cloudy day, so the actual production. But you can see here the difference between the winter and summer, of course. The same with the wind. This is the wind in winter for this year, same year, same day, and this is the wind in summer, okay, which is on average is lower, okay. The wind speed. So to illustrate the seasonal imbalance, I use the same case. This is the same case I put before, the same case, but I have assumed that the renewable installed capacity is multiplied by 3. So in this case, the production of January 2017 we multiply by 3. And of course, at some moment of the day, the energy was excessive, so we should store energy here. But most important, the energy was insufficient for several consecutive days. The energy was insufficient. Okay, and the prices were very high, by the way. These are the prices, but anyway. So no matter if we multiply by 3 the installed capacity and we have 270 gigawatts with a probably 76% energy share, there are moments that you need to recover energy that should be stored in the past. So this is very, very, very challenging problem, the seasonal storage needs. Okay, this is a challenging problem, the most challenging problem, along with the investment challenge I mentioned earlier. On the transmission level, I will illustrate also with some example. On the transmission level, there are some challenges. For instance, the distance, as we still will resort to centralize the renewable, for instance, the China example and the India example, I gave you 900 megawatts of PV. So we will still using centralized generation, hydro, for instance, like in China, and then the average distance between the major load center and the big, like the northern Africa or the North Sea from the wind generation. So there will be longer distance. We will need probably a lot of new HVDC grids or overlay grids overimposed on the AC existing system. The system stability will be threatened because of there's a possible sudden disconnection. For instance, there is strong winds, and there are strong winds, and the wind machine disconnect to protect themselves, or the clouds with the PV system and the like. And so far, the capability for control, reactive power voltage control is rather limited in the past so far. This will improve with smarter interfaces, which belongs to the solution I'm going to mention later. There will be more network congestion of the existing system. This is happening already in Central Europe. Germany has a lot of, in the central hours of the day, they have a lot of PV. So the power flow with the neighbors are changing daily, twice a day, exporting and importing and this kind of thing. As a matter of fact, Belgium, for instance, is now deploying phase shifter, and other countries, in Poland, phase shifter to protect themselves with these low flows. So this is a complex problem. So overall, this means that we will need more ancillary services, more flexibility. Conventional generator, nuclear generator, or big thermal generator will not be flexible enough to follow this renewable production. So the whole concept of base loading, intermediate loading, and peak loading, this concept is totally vanishing. So there is no longer of application in the future where there are so many renewables. This is an example of a voltage dip in Spain. It was a problem in the early days of the wind energy, because with this voltage reduction, this major load, this lapbacks in Spain, basically. So when there is a short circuit here, the voltage gets reduced significantly. Even in the south of Spain, the voltage don't recover fully. So this affects the whole country. So this happened yesterday, many years ago, in 2007, at the beginning of the era of wind energy, when the wind generators were not so sophisticated as today. So they were not able to withstand voltage this, and there was a sudden disconnection of 1 gigawatt of wind energy. So because of this, the grid code were reinforced and made more exigent, and now in Spain, all wind energy farms should withstand, with a grid code, the voltage dips. This was in the early days. But this continued to be a problem. For instance, in Australia, I don't want to stop here so much, there was a very huge blackout in South Australia affecting nearly 2 million people owing to voltage dips, because there was many thunderstorms, tornadoes that brought down high voltage poles, and each time this was a voltage dip, a short circuit. So there were quite a few consecutive short circuits, and those short circuits were, detected by the wind farms. And there was a software that after a few voltage dips, they disconnected. So they withstood the first voltage dip, but not quite a few. So at the end, there was several voltage dips, a disconnection of the wind energy, in combination with the interconnector was also switched off. So at the end, there was a big blackout in Australia because of the voltage dips. And it was last year. Okay, let's move because I'm probably getting late, to the distribution side. The distribution systems are quite different. This is a summary of distribution system. These are radially operated. We have normally open section that can be useful for giving service alternative routes in case of fall or something. You can feed this feeder from this secondary substation from this side. So these are the typical topology. They are designed for power flow from the substation to the load, unidirectional power flow. And usually the simultaneity coefficient is rather low, probably less than 0.5, 0.3, something like this. So this is the problem that may arise with the high penetration of distributed generation. This is actually happening. When there is a distributed generator, we may have a significant voltage rises. And when there are electric vehicles, for instance, with fast charging, we may have a congestion or voltage drops, unacceptable voltage drops. This kind of problem, this is what we are facing in distribution system because of the renewable penetration and the electric vehicle penetration. The major problem. Okay, now the last part of my presentation. What can we do to try to prevent this problem, these technical barriers? Again, I have divided by generation, transmission, distribution, and storage in this case. The solution are for this. So I will go quickly over this part of my presentation. To begin with, renewable generators should have been equipped with smarter interfaces. So thanks to power electronics and the appropriate controllers, we can manage renewable generation in a more efficient way, particularly if renewables have built-in storage. If renewables don't have storage, so the control capability is much more limited. But if we, for instance, there are PV with renewables, we can behave much closer to the conventional synchronous performance. So this is what I'm doing here. Renewable can contribute to ancillary services, even if there is no storage. So they can perform voltage regulation, some kind of frequency regulation. They can emulate synchronous machine if they have a storage. I hope that somebody else will talk about, so I don't want to stop here so much. And also, they should be equipped with black start and with grid forming capability, which also somebody probably will talk, Rodrigo, somebody else will talk about this later. So I don't want to go into the detail. But I've been stressing in red continually the need for a storage system. I mentioned earlier in the generation, and now here the renewable. A storage system will be needed for seasonal and for daily storage. On the transmission side, we should significantly increase the number of power electronic devices, FAT devices, also conventional phase shifter, which are very complicated devices also and very fragile devices also at the same time. We should increase the power and voltage rating on voltage converter with IGBT DC lines. Hopefully, there will be a multi-terminal way of building overlay grids with the HVDC lines. I don't know if we will mesh or not. We should improve the grid codes, which is something which is being worked now. On the NSOE, for instance, in Europe, this is a very hot topic, improving the grid code standardization, so that everybody, in order to promote the interconnection of all countries, we should be sure that everybody has the same grid code. And it's one of the main topics we are working on here in this department, the advanced energy management system, distribution management system, advanced application for energy management system, so that we are able to monitor and to control wide areas like the European area. For instance, now in the winter package, the European Union is promoting the notion of regional operational center. The regional operational center is will be hopefully in charge of coordinating the national TSOs, even though the TSOs are not very happy with the idea. They are complaining. They are writing position paper against this idea because they already have other notion they created, NSOE created. And we will have new technology like synchrophasor-based wide area control. Again, for ancillary services, considering the volatility and the uncertainty of the renewable, we should need also the transmission system operator will be very happy if they were capable of managing a storage system. For instance, in Spain, the transmission system operator is struggling with the regulator in order to get control of the pumped storage system we have in Spain, which are currently so far managed by generation companies. So this is important. Now some example of these technologies. For instance, this is now a very old slide, appeared in Spectrum in 2013, showing the Germany plan to provide renewable energy from the North Sea to the downtown, to the down industrial region of Germany. Okay, this is now in trouble because there is a lot of wind energy, but these lines are not still erected. They are not actually. There are a lot of social opposition. There is somebody here from Germany that can probably explain better than me. And some those section of those lines are being now redesigned for being underground. So this is a problem. But this is the idea of HVDC in Germany. It was the idea, I don't know now. In China, for instance, there's an overlay HVDC grid which is being built above the existing AC system. This from this region, Yunnan to the east region, there is a synchronized area. And they are linking the west side with the east side through 2,000 kilometers, over 2,000 kilometers, plus minus 800 kV or even 1,000 kV lines. There's a very long HVDC corridors, okay? And these are creating a lot of problems because this is threatening the stability of the AC system, the underlying AC system. Because, for instance, if one of these big lines suddenly disconnect for a problem, the 3 gigawatts of energy it is carrying should suddenly move to the underlying AC system. And the underlying AC system will collapse immediately because it's not able to carry this huge amount of energy. So for this reason, there will be a collapse, and now the Chinese are splitting a system using back-to-back connection here, so that this no longer synchronous with this. There is a synchronous area. So what has been so far synchronous area are being split into asynchronous area linked with back-to-back converters, so that to prevent regional cascading in case of failure of HVDC system. So this is a problem that was raised in the EDC. An abundance of high voltage DC makes big AC grids unstable in the spectrum also, because you cannot read the fonts from the back of the room. Multi-terminals also, there are some examples of multi-terminal which have been built currently, like this one in PGN in the east coast of USA. This multi-terminal grid in the future will play several roles. For the time being, it is being used for integrating offshore energy into the mainland grid, but in the future it will serve also as an overlay grid, because there are congestion here, and you know that they are using locational marginal prices, unlike in Europe. So the prices are different because of the congestion, and so hopefully the different prices will be useful for paying this deployment of HVDC line, because they will be helpful to reduce the prices, so to say. So there are several purposes of this line, of this multi-terminal system. I mentioned also the need for using more sophisticated energy management system. There will be new energy management system, and there will be many more interaction between those management systems. In the past, we simply have the energy management system or the transmission system and the very, very rudimentary, very simple distribution management system for distribution companies. But now, in addition to those systems, we will have what we also have in the past. Big generator have also its own generation management system to follow the ancillary services and the production and this kind of thing of the market production. But now in the future, we will have a management system for renewable, the power plant controller. We will have for prosumer local home-based management system or building management system. At the substation level, the digital substation, we will have substation management system, because you will have a lot of information provided locally by synchrophasors and this kind of thing. So we will have substation management system. We will have to interact much more with the neighbors, because there will be regional markets, like in Europe. You know that in Europe there is the internal market, which is working since 2014, and now this market is wholly developed for 90% of European population. So this is you need to interact with your neighbors. This is the idea of regional operational center, of helping the coordination of transmission system operator neighbors. So this will be a much more complex world than in the past. There will be many more agents and many more interactions and new roles. This is an example of the substation management system. Thanks to the 61850 standard, which is a standard for Ethernet communication inside and outside the substation. So you will be able to collect and gather much more information than in the past at the substation level. And sending all this information to the control center is virtually impossible. Okay, so you will need probably to have an on-site management system that should be called substation management system, previously processing the raw information and then sending to the external world only the information which is really needed and cannot be locally processed to coordinate with the other substations. So in our opinion, we have been promoting for the last 20 years the idea of substation management system. And it seems that in China, for instance, they have already developed some pilots of this idea, but still under development. It's not yet a reality. This is an example of the energy management system developed by Red Eléctrica, the Spanish transmission operator, which is called SECRE. Here this is the SECRE, and on the other side, on the right, you can see the SECOEL, the conventional center that they have before. So this is an add-on center devoted exclusively to renewable, mainly wind energy in the case of Spain. So they are making forecasting, they are analyzing whether we have enough reserves, we are analyzing congestion of the tie line with the neighbors, and in case of need, they have the capability and the authority to reschedule wind energy production. reduce, for instance. Sometime during the night, when the load is very low, we have to reduce the energy production. So this is performed from this center. I will skip this because this is what I have said. The function performed on this center, this congestion, rescheduling of production in case of if there is enough reserve. This is what I have been discussing. I don't want to stop here because I'm afraid I'm getting late. So on the distribution grid, we are also improving many things. Of course, we are deploying power electronic devices. We are enhancing distribution automation, which is a notion, very old notion that in the past was very expensive, and now with the digital world, the ICT technologies are much cheaper, and so we are capable of finally implement in practice this distribution automation idea, which has been in the air for many years. We will have smart meters, and so thanks to this information, we will be able to finally again have a true DMS of the distribution system, distribution management system, because what we have had so far, I don't think it can be called distribution management system. It's basically a place where you receive calls from the customer in case there is a blackout or something like this, but this is not very sophisticated. So thanks to this kind of information, we will finally have a true distribution management system, where you can, for instance, perform a state estimation. Also, this will implement a new function, which are also very old, theoretically, demand management. The demand management is a very old concept. But now, thanks to the distribution generation, electric vehicle and the like, and I don't want to stop here because I'm sure that this is very related with the microgrid, so I don't want to stop here. Microgrids and local markets, efficiency improvement, this kind of thing are also hot topics that will be helpful to enhance the capability to introduce more and more renewable energy in the distribution system. And finally, in red, again, distributed storage. So this, I've been putting in red every time I'm talking about storage because, in my opinion, storage is the key point. Well, this is EAMI. I will skip this slide. Distribution automation. You can see this is taken here in Andalusia. More and more antennas like this, showing you that this is teleoperated, remotely operated, so you don't have to go with the car to manually switch off. So this is manual, remotely operated, and this is a communication channel that can be used for fault passage detectors, for instance. So this is a possibility of enhancing the information you have and performing, for instance, state estimation. And this is a seasonalizing station where you can see also the antenna. So this is more and more common because of this is cheaper and cheaper to deploy digital communication system or using public wireless communication channel like 4G, for instance. Also control power electronic devices. We, for instance, have been promoting the use of, in this group, the use of back-to-back voltage source converter linking asynchronously one feeder with the neighbor feeder. This is one feeder, this is another feeder, and we can link the two feeders with a DC link, a synchronous link, with two back-to-back converters that have 3 degrees of freedom. You can control freely within the ratings of the device the active power flowing from one feeder to the neighbor. We can control at the same time the two reactive power on both sides so that we can regulate the voltages on both sides. So these are 3 degrees of freedom. And this can be used, for instance, consider the other example. There was an overvoltage here because of excessive injection. There was a congestion here because of excessive consumption of fast-charging electric vehicle. And then if we use this link here, which is a way of asynchronously and flexibly linking, closing the loops, it's a flexible loop, so to say, we can move energy of this generator through this side and can be used for charging the vehicle. So we could eliminate the congestion and we could eliminate the overvoltage, for instance, because of this DC link, asynchronous link. Okay, so this is an idea that we have already tested in the lab and is working, and we have simulated, of course. Another idea that we have been also developing, we are now almost at the industrial production level, changing the mechanical taps of secondary substation, the secondary transformer. They have mechanical taps. They can change mechanically plus minus 5%, plus minus 5% of the voltage level on the medium voltage side. This is on the medium voltage side. This is a dry transformer. You can see here the triangle, the delta connection. Replace the mechanical switches by thyristor, okay? This would give you flexibility to change in the tap, which are fixed. You can see the mechanical bridge. This mechanical bridge is fixed. Once you put the transformer in service, there is no way of moving it unless you go on to disconnect the service and move it. So this is seldom done. This is seldom changed. If you replace the mechanical switch with thyristor switches, you can do it as many times as you want, as frequently as you want. So this gives you flexibility to regulate the voltages on the low voltage side. So, for instance, here, if there is a voltage problem here, you can regulate the voltage so that the low voltage is screened from the medium voltage variation. So there are tap changes, so you can strategically locate tap changes in those places where you have voltage problems, okay? I will skip this example. This is an example this example is intended to show you that an initial situation, radial configuration, where there is a limitation of PV penetration of 82 megawatts, if you add DC link, asynchronous link, as you add 5 transformers with tap changer, you can increase almost 30% the capability to integrate photovoltaics just by adding hardware. And you don't have to upgrade the feeders, for instance, because if the feeders are urban, you need to dig the sidewalk, and you need to spend a lot of money in replacing or augmenting the capacity of the feeder system. The same can be said with fast charging. The fast charging, you can use a vehicle charging conventionally with individual chargers, but you can adopt a shared DC bus fed by adjacent feeders, so the DC bus acts like the DC link, so you can have more flexibility to perform fast charging of a fleet of vehicle without congesting the feeder. So the same idea can be applied to fast charging of vehicle. I would like to have some time for questions, so I will skip this. I was just telling you that we can perform state estimation, and this is a pilot project we are carrying on in Malaga City, in Smart City District, where they have deployed 12,000 smart meters, and we are now and some sensors in the secondary substation, so we have enough information to perform a state estimation, and we have, for instance, obtaining something like this. We have obtaining a lot 24 hours. We have the losses, for instance, the losses of the 3 phases and the neutral cable. So this, I don't have time to stop here. I have too much material. Also, microgrids. The microgrids that is the topic of this workshop, so I will skip this slide. So, a few words about storage, and I will finish. I've been marking up in red every time I was mentioning the need for daily storage and seasonal storage. So there are 2 kinds of storage, and there is no clear border or clear frontier between both of them, the centralized and the distributed storage. So everybody wants storage, but it's not clear who should pay, or it's not clear what say the regulation. The regulation is not clear yet. So in the future, there's some uncertainty about how the regulation of the storage will be made in the European Union. It's not yet clear. So all lobbies are pursuing for convincing the European Commission that the storage should be regulated in a different manner. So the question is, for instance, so far in Spain, we have only large-scale storage with pumped storage. It's controlled by generation. But the transmission operator wants to also have something to say about this pumped storage. So it's not clear how should we deploy the storage, when, as soon as possible, according to the penetration of renewable, and where. Centralized, distributed on the consumer side. So there's a self-storage. So there's many possibilities, and it's not clear which proportion of the storage should be at each level. It's not clear. It's a huge optimization, planning optimization problem, and regulation problem. Okay, we have very few. We have only 145 gigawatts of storage, which is barely 2.5% of the installed power so far. So very, a majority, 97%, 98% is pumped storage. So we still, the storage is still in its infancy. So it's not very far away from the pathway for storage still to grow much more if we want to increase the sharing of renewable. Otherwise, it will be impossible. So I will skip this. just will finish with this, because I don't want to, 1 hour now speaking, so it's too much for you. You are thinking of the coffee right now, particularly those who have the jet lag, like Rodrigo. So just to finish, that the 21st century paradigm is becoming much more complex on all levels, generation, transmission, and distribution. So generation will be mostly composed of renewable and probably nuclear, depending on the country and on the regulation. More renewable will have local storage, built-in storage. There will be transmission, also they would like to have pumped hydro, some kind of storage. Distribution, there will be some distributed generation, PV generation with storage. There will still cogeneration, larger, not distributed at the customer, but medium voltage cogeneration. The generation will be more diverse, and the capacity factor will be much lower. For instance, in Spain, combined cycle, the capacity factor is less than 10% now. So this is ridiculously very low compared to what they planned when they built the combined cycles. So this is a problem, because the prices have been reduced, and it's difficult to get the investment to get them. So the transmission will be not only AC, but a combination of AC-DC, probably with the system with an overlay system, mainly DC system. There will be more intelligent, more interconnection with other agents, so there will be much more complex. There will be prosumers, so microgrids, local markets, aggregators, this kind of virtual power plant, or this kind of acronym all of you are familiar with. So in summary, the future will be much more complex, and this is good for all of you, for all of us who are devoted to working and researching in power systems. So power systems in the future will not be like they were in the past, that was seen as something, obsolete and lack of interest. So it's a challenging and very interesting future for us, brilliant future for us. So Edison was a very smart guy. He was, apart from being a prolific inventor, was a businessman and a visionary. And so he, when he was old in 1931, he was warning, we should pay attention to solar energy. So thank you.